some factors affecting rock velocities. Rocks are heterogeneous material, right? And a lot of different kinds of rocks. They're made up in lots of different ways. We're going to be talking about the kinds of things that have been shown by laboratory measurement primarily to affect velocities of rocks significantly. And the three of them are, let's just go back, composition, stress, and architecture or microgeometry. Okay, I'm going to start by just making some bold-faced statements. Composition. What are rocks made out of? Porous rocks. We're interested in those reservoir rocks, right? That's what we're going to have in fluids and different kind of fluid. What are made out of? Solid components, and they're made out of fluid components. So one might think that since the velocities are dependent upon the spring constant, the volumetric spring constant, the stiffness of the rock, the bulk modulus of the material, one might think, well, it's going to depend on the bulk modulus of the material out of which the rock is composed. And the bulk moduli of those materials are of fluids and of solids. So I'm going to start with solids, and I'm simply going to state that for, it's complex, but in general, particularly for consolidated rocks, the larger the mineral modulus, mineral bulk modulus, the higher the wave propagation speed. That's not hard to understand. If you've got a wave propagating in one dimension and you have a stiffer spring, you've got a higher velocity, and the same is true with our elastic wave, plane wave propagating in three-dimensional body. There is a table in your, Mike showed you at the top of your web page, where you can go to the appendix, or supplements, I guess it's called, right, Mike? And in that supplements, there's an appendix 1. In that appendix, there's a table. I can't show it to you right here, but maybe we can do that after lunch or something like that. In that table, the elastic moduli and the density of typical minerals, yeah, that's great, are listed. And you will see that there's a variation in those materials. In common sedimentary rock minerals, let's say calcium carbonates, silicon dioxide, and hydrite, things of that, dolomite, things of that nature, there's about a factor of 2, maybe 3 at the most, in bulk moduli of the different minerals. Sedimentary rock minerals, that's what I said, you're a factor of 2, something like that. The moduli of solid material are much larger than the moduli of fluids, which in turn are much larger than those of gases. Gee, great revelation. I talked about compressibilities before, bulk moduli here. You'll see slides that I'm going to talk to you about, or those 10 to the 10th dynes per square centimeter. I use CGS units, which are not very popular these days, but since I'm an old fogey, that's what I use. What does that mean? Silicon dioxide has a bulk modulus of something like 38 times 10 to the 10th dynes per square centimeter. It means that in order to change the volume by 1%, you would have to apply a stress of 55,000 psi, roughly speaking. 55,000 psi corresponds to something like 25 miles column of water. So go down to the bottom of the Marianas Trench, find that pressure and multiply it by 4, and that's how stiff that spring constant is. That kind of pressure will produce a 1% change in the volume of silicon dioxide, isotropic average. Well, just for comparison's sake, water, which you've all heard in your life, is an incompressible fluid, right? One of the more incompressible fluids there are. About 4,000 psi will generate the same result. So now we're talking about 8,000 foot of water, something like that, which is deep. If you've done any snorkeling or diving or what have you, you know that's deep. But it's not the same as 55,000. And for gas, even gas at reservoir pressures and temperatures, typically 7,000 or 8,000 feet, let's say methane, something like 500 psi will produce the same 1% change in the So solids are really stiff springs, fluids are less stiff, and gases are, even at high pressure, are really pretty weak. Okay, the values are known. That's what that table's about. Thank you, Mike. Composition, what's the other part? Fluids. We talked about the solid part of the rock. Fluids. Here's a picture straight out of a paper by Wiley et al., Gregory Gordon, I think, from 1956. What they've got plotted on the bottom is porosity of the rock, and on this side, velocity in a nonlinear scale decreasing, okay, going down, or increasing going down, decreasing going up, because these guys, petrophysical engineers will really like this, like those transit times. So they have linear transit times, okay, over here. And what they did is they took a bunch of sandstone cores and they put no stress on them at all. They just attached transducers and propagated ultrasonic waves through them, impressional waves through them. But for each core, but they had cores of quite different porosities, they made a measurement of the dry rock and a measurement, and a measurement of the water saturated, of the rock when it was saturated with water as well. You see that over here, water saturated, open circles are dry. Now, I want you to look at these. Here's a pair. So all these things should line up. There's a pair. This one doesn't, they weren't able to get a dry measurement. Here's one, here's another one, here's another one, da-da-da-da, okay? So this isn't the best way to compare things, but what I want you to notice is all the dry measurements are higher in the plot, that is lower velocity, than their corresponding wet measurements, the dry and saturated measurements. And there are significant velocity difference here. You know, what's this? Well, that's a lot. That's 8,000 to 12,000 feet per second. Big difference. Not small difference. So a significant effect on velocity comes from water, comes from change of fluid, as a result of the change of fluid, air, dry, and atmospheric pressure. I talked about 500 psi. Well, you don't even, I don't even know what it is. I haven't done that calculation, but it's probably a psi or something, or even less, to produce a 1% deformation of air at atmospheric pressure. So, at constant solid composition, in each case, and at constant stress, both are measured at the same stress, and at constant architecture, it's the same doggone rock in each case. It doesn't have a different geometry to it, the pore structure. The fluids make a difference in what the velocities are in porous rocks. Okay, at constant pressure, for a given architecture, velocity increases. With increasing bulk modulus in the minerals composing porous reservoir rock, I should have said at constant pressure for a given architecture and for a given fluid. That certainly is true. And at constant pressure for a given architecture and with a fixed mineral composition, velocity increases with the bulk modulus of the pore fluid. Our brine saturated rock velocities were higher than our air saturated rock velocities. Okay? And brine has a much higher bulk modulus than air. Okay, next we have dependence of velocity on pressure. Now this is a little more complicated slide, so let's again look at the abscissa here is simply the external or confining stress. Now we're going to take a rock, core, again in the laboratory where we can control conditions. That's what's so nice about the laboratory. And we can jacket that rock and put it in a bath, a fluid bath, close up our pressure cell and pump up the pressure on the fluid. And we can isostatically compress that rock. We can also attach, let's say this is my core, we can attach a transducer up here, transducer down there, bring the wires out of the cell, and pulse the rock and look at what velocity we measure, longitudinal velocity we measure, compression rate velocity. Okay, so let's suppose we do that. There are two cores here. They tell you what they are. One is a 17% porosity sandstone. The other's a 29% porosity sandstone. This is the lower porosity. This is the higher porosity rock. Let's concentrate on this one. It's more easy to see. It's a bigger effect. The solid curve represents doing that with, this is, by the way, from a paper by Hicks and Barron, the same year, 1956, where they had water in the rock, but they did not change the stress on the water. So the rock was jacketed, and the water, the pore space had a tube that came out of it, and it was at atmospheric pressure all the time. What they changed was the external pressure on the rock, and that's what they're plotting against here. And this is the curve they got. It's a huge change in the velocity, just like for our fluids before, several thousand feet per second, less than 10,500 up to 13,500 at 6,000 psi. Okay? Then they did some further experiments. They said, well, let's suppose we just took it up to, pick one, there's 2,000, 3,000. Let's take it up to there, and then from that point on, we'll raise the pore fluid pressure by the same amount that we raised the external pressure. So here's the external pressure over here. We moved it over 1,000 psi. This goes with 3,000, so that's that guy. This goes with 4,000, right? And they raised them by the same differentials. So they kept the differential pressure, external minus pore pressure or internal pressure, constant. And what happens? The velocity stays constant. Same thing really down here. There's a lesser effect, but it's the same in character. Other people have seen this too. This experiment was repeated a lot by different people on a lot of different sedimentary rocks, including other sandstones, etc. Same result. So what do we know from this? We know that velocity is going in a porous sedimentary rock is going to depend upon stress, and it doesn't just depend on the external stress; it depends on the differential stress. The external or confining stress less the pore fluid pressure.
Let's just talk about that just for a second to make sure that you really understand what's happening here. Is that, let's go back to the previous one, Dave. And this is sort of take a particular point, like right here. And I don't know, Terry, I mean, at this point, what would be the particular pressure that we would be, or what would be the particular pore pressure that we would be putting in it? What would be the pore pressure at this point? Let's try the easy one. What's the pore pressure here? Zero, right? Okay. So we've just gone and increased the confining pressure 1,000, 2,000, 3,000, 4,000 psi, and we have zero pore pressure. Okay. If we go to this point, what's the pore pressure on it? It's 1,000. Okay. What's the confining pressure? Okay. What about this point?
9.
What the pore pressure is?
5,000.
1, 2, 3,000, right?
No, 4. Let's
Okay.
get one.
Okay, okay, so it's 4,000, right? Okay, and all we're saying is that the amount you effectively squeeze the rock, okay, if the pore pressure equals the confining pressure, we're not squeezing that matrix at all, okay? Okay, but if the pore pressure is less than the confining pressure, okay, we are squeezing it. And all that matters is the amount of squeeze is the confining pressure minus sort of the supporting pore pressure, okay? And what's happening then is that these rocks sort of squeeze together and become more rigid, okay, as we effectively push on the matrix. And again, it's sort of what's called the effective stress, or the delta P between the two, is how much you're squeezing the rock, okay? And you'll hear us talk about this. The reason why I, again, sort of stopped here is that this is sort of the determining thing in terms of the compaction state. How much have you squeezed that rock? And because the more you squeeze it, the more rigid it ends up becoming. And what matters is the effective stress, or the difference between how hard you're pushing on the matrix, and how much support you're getting from the board line.
Is there a similar sort of thing with shear waves?
Yes.
Makes sense.
The answer is yes. The effect is smaller, but the same effect. Differential pressure is what matters.
How do you maintain the pore pressure? I can see, I mean, if you press a sample, that's a confining pressure.
As
The
the
pore pressure,
experimentalist.
like pumping water into the rock.
All right, here's how you do it.
Yeah.
You machine some, say, stainless steel heads to which you attach with cement the transducers. You have to have your whatever kind of transducers you're going to use. But running through the head is a stainless steel tube which you weld it on to the end piece, and the stainless steel tube comes out the pressure cell, out the top of the pressure cell. Got to have a good pressure seal there, but that's doable. It takes a lot of time screwing around. That's what we do in physics. So you now have an independent control. Just put a valve on it and a pump. An independent control on the pore fluid pressure, the pressure of the water inside the jacketed sample, and a pump that is controlling the hydrostatic fluid that surrounds the jacketed core with its two end pieces. Okay? That's how you do it. Okay. So we already went through that. And it's true for shear as well as P.
Also, another reason why I'm sort of talking about this is that we're getting into issues around Stuybarrow and 4D rock physics, okay? And that
I want to make one.
Yeah,
Go ahead.
And you have to remember what happens. You just go back to that other particular plot. If we were sort of gone and we're sitting at one of these points right here, okay? And if we go and don't change the confining stress, okay? And just go and say, hey, I want to go and start changing the pore fluid, okay? And releasing the particular pore fluid associated with that, okay? That, which way?
You want to go this way.
Yeah.
You're going up that.
Yeah, that.
You're going to go from here to here is what you want to think about.
Or you can go from here up to
Yeah,
here.
right, exactly.
And so what you end up doing in that case is you move up on one of these curves, and you end up seeing that or actually, if you depressurize it, you end up coming down like this, and you'll end up seeing a change in the rock velocity associated with reducing the pore pressure, increasing the effective stress, and causing the rock to compact, okay?
If you, this is the point I was going to make too. Let me just make it again, and that is, if you notice that this curve rises most steeply down here at low differential pressures. Low differential pressures occur in a normally pressured section in the shallowest measures. Right? You don't have much confining stress. You don't have much pore fluid stress. The difference is not very much either. That's great. When you get deeper, you have this whole overburden of rock, of density 2, and connected with the fluid in one path or another, for a normally pressured system, you have a big fluid column with a density of 1, water. Okay? So the differential pressure goes like the density of water. Well, the density of water at 1 gram per cubic centimeter is 0.435 psi per foot, a useful thing to remember. 0.435 psi per feet means at 10,000 feet, you have 4,350. We'll say it again for the camera.
Yes.
But if you're up here, just notice that the curve flattens out. And so if you release the pore fluid pressure, as you do when you suck on the well and try to produce your fluids, up here you don't get near as big effect for the same amount of change in pore fluid pressure. This is a 4,000 psi change. Okay? As you do if you have a very highly overpressured but deeply buried rock, where you would have a high fluid pressure, and you're down here with the differential pressure. Now you come up 4,000 psi, and you're up here someplace. So you get a much better effect for the lower differential stress initial state. All right, we went through this. We established the second factor. Composition, both solids and particularly fluids, affect the velocity of porous rocks significantly. So do stresses, and in particular, the differential stress is what affects the velocity of rocks. And the velocity increases with the differential stress. Now we're going back to this slide, same slide I showed you before, but now I'm going to use it for a different purpose. I'm going to talk about architecture. What do we have in this slide? Well, we went through it before. We've got porosity changing down here, and transit time increasing this way, velocity increasing down. Let's just look at these water-saturated measurements. They're all sandstone cores. Composite, they're all water-saturated. Solid composition, silicon dioxide, same mineral. Fluid composition, water, same fluid. Stress, same stress, zero stress. No differential pressure in any of these measurements. But the velocities are changing. At low porosity, 15, 16, 17, something like that, 1,000 feet per second, and at high porosities, 8,000 or something like that feet per second. These sandstone cores. Gee, great revelation. Physical engineers have known this forever, you know. In fact, one of you pointed this out among others. And so we have another thing that affects the velocity of rocks, and that is the character, the geometry of the pore system, or the architecture of the matrix. Mike was talking about you're stressing up the matrix with that differential pressure. The skeleton of the sandstone or carbonate or whatever porous rock you're dealing with. And porosity is one characteristic of architecture. All right, I'm trying to get this across in a way. What does that mean? Any of you like antiques? You go into stores, you like antiques? Okay, you go look around, see a bunch of junk. Sometimes you see furniture made at different epochs, let's say from 1750 to now. And there are different design characteristics. You see a table. Sometimes a table may be elegant and thin-legged and nicely braced, mortised. And you may say, well, that sure is an elegant design. The tables might have those nice steel legs, lots of leg room, pretty spacious design. You go see a table that's made out of solid wood, a farmer's table, let's say. I want to tell you, it's got a lot more bracing and a lot heavier members, etc. A lot more material, partly because the wood isn't as strong as the steel that table is made out of, and partly because of the design of the fellow architect who designed the table and said this looks more graceful or whatever he was trying to achieve. That's why I call it architecture. And the porosity would be, what is the volume of the envelope of that table that isn't occupied by solid material relative to the volume of the envelope. That ratio would be like the porosity of the rock. The part that isn't occupied by the solid divided by the envelope of the rock. That's what porosity is. So we have one more thing that affects velocity significantly, and that is the character of the rock structure. A principal component of which is porosity. It's not the only possible component, but porosity is the biggest one. If you know the porosity, you know a lot about how much the architecture is going to affect velocity for most sedimentary rocks. Not as true for carbonates as for sandstones, but true. So we have three things.
Just sort of ask a question. Can anyone else think of something else about the architecture of the rock that could influence its velocity other than porosity?
Mineralogy.
Sorry?
Mineralogy.
Yeah, well, that's not the architecture now, that's composition.
Segmentation.
What's that?
Segmentation.
You bet. That's a good one, Mark. If you had a bunch of balls, equal size spheres of a mineral, and that's one architecture, and you're just squeezing on them, And a different architecture is to have, let's say, cylinders, but they're welded together somehow by cement. You could have the same porosity, but you have a different geometry. And you would have a much more stiff spring to propagation in the direction of the longitude of those cylinders, let's say, for example. So cementation is certainly, right?
Yeah. Well, just sort of think, if you go and take a porous rock, and what's another, let's say, core measurement you always are thinking about making? Has
Sorting.
something to do with the architecture.
Sorting?
Is it
Sorting?
sorting? Yeah.
That's close. Permeability is
Sort permeability, but yeah, no, sorting is another thing, and in fact, I mean, it's a subject of a paper sort of built off the Cascade board, and we'll get back to that in sort of a later lecture. But sorting is something else. I mean, that changes the architecture or the appearance of the way it looks. It's good.
Okay. The important thing in this sentence is the velocity decreases with increasing porosity, okay? You all knew that ahead of time, but it's an architectural thing. So, I'm not going to repeat them. That's what's important. There are three things that have been found experimentally by multiple authors that significantly affect the velocities in porous rocks, and those are what they are. And I guess this is about where we break for lunch, right, Mike?
Yeah, I think we've done the check.
No, wait, I've got a little more to do here. Good, you check and I'll talk. This is a sort of a biggie. This is the real general problem of interest in exploration. We talked about, I want to look at those porous rocks, the reservoir rocks. How do rock velocities depend on the properties of constituents? Well, we talked about what they are. What we're really interested in hydrocarbon exploration is, in particular, how do they depend on the pore fluid properties, right? That's what we really want to know. We'd like it to be the case that velocities depend, in the porous rock, depend a lot on what kind of pore fluid you have and in the way that we can determine. Because if that's the case, since velocities and densities go into the reflection coefficient, that's what determines the normal instance reflection coefficient. Our reflection amplitudes could tell us something about what kind of pore fluids we have in the ground. That's what this is all aimed at. So let's talk about that. Gossman wrote a paper in 1950, I believe it was, in which he just looked at the equations of motion. He actually did a static analysis, if you like, of a system, of a porous system. And I'm not going to go through a derivation here. We cut that. We did that last time. For those of you who were here 6 years ago, you can all inform your teammates. But the Gossman equation, which you're going to see in a moment, what his result was that the velocities depend on the grain properties of the grain material, elastic properties of the grain material, the grains I call solid material. That depends on the elastic properties of the pore fluids. Gee, what did we just get done saying experimentally? Those two are compositions. And it depends on the properties of the matrix or rock framework, explicitly on porosity, and also indirectly on porosity as well. The stress dependence I'm going to leave open for the time being. I'll come back to it in a little bit. These are Gossman's equations written in terms of a whole bunch of stuff which is explained down here. I want to go through these a little bit, just so you got them all. This is the equation for the compressional wave speed in this isotropic and homogeneous, macroscopically homogeneous and isotropic porous medium. And this is the shear wave speed equation. In this case, we know that the shear wave is mu over rho. The square, V squared is mu over rho. It's also mu sub m. What's m? M is a matrix, the property of the matrix. The matrix is the evacuated frame. You imagine you put a saran wrap over the frame of the rock and you evacuated, put a vacuum pump on it and took everything out of the pores. Okay, nothing in the pore space. And then you performed your squeezing experiment and said, oh, what's the bulk modulus of that being? Well, that's what in this case, the shear modulus, measure the shear modulus. That's what this what an M, a subscript of M quantity is, a property of that evacuated matrix. So you've got grain parameters, solid parameters, there, and in the density, or G, this is the density of the bulk density of the rock. You have fluid parameters, K sub F and rho sub F in PUA. And you have matrix porosities, the sigma sub M, Poisson's ratio, and the beta, K sub M. And you also have explicitly porosity. Okay? That's everything that's here. So let's just say what some of the conditions. You know, when you derive an equation, you have to start by making certain assumptions. What am I dealing with? What kind of a system am I dealing with? And so here are some of the critical conditions for validity of Gospin's equations. They apply, first of all, I said it was a static analysis. One can derive Gospin's equation by a static analysis. That means the low frequency limit. I ask, put the stress on the rock, ask how it's deformed. That's the ultimate DC. Okay? Well, what does low frequency mean? In terms of, with respect to what? Low frequency with respect to what? BO came along in the mid-50s and he did a proper analysis of the transient response, of the time-dependent response. And for the reasonable porous rocks, how should I say this, for the kinds that we deal with in crustal geophysics, the characteristic frequencies of transition are up near, between 1 and 10 megahertz typically, well above even the highest logging frequencies. There are some rocks where you could get down into 100 kilohertz or so, still higher than logging frequencies. And seismic bandwidth is 10 to 100 hertz, prospecting bandwidth. We are in the low frequency limit for seismic, so this is okay for us. They apply for elastic deformation of a macroscopically isotropic and homogeneous elastic body. What the hell is that? Macroscopically isotropic and homogeneous. Let's think about a porous medium. If I'm a little, what's the name of that picture? Where they have the Raquel Welch and Donald Pleasance, who was the bad guy, and they were inside this guy's brain. This Russian physicist had a fantastic voyage. You've seen it. Some of you may have seen it. They shrunk these guys down and they go in there in the blood system and they go in the brain. They're going to fix this guy's brain up. Okay, they have to deal with white corpuscles and everything else. Well, imagine yourself one of those microscopic characters inside a porous rock. You get inside a pore, and every direction in which you look is fluid. And it has certain properties. Well, it may be isotropic, but if you move over about 1 millimeter, you're inside a grain, and every direction you look has grain properties. And they're not the same as fluid properties. So that may be isotropic there too, but it isn't homogeneous. It's not the same everywhere in the rock. So macroscopically isotropic and homogeneous means if I take a small enough, a small segment of the rock, small with respect to the wavelengths I'm interested in the elastic propagation, and average the properties in that small volume element. Let's make it a cubic centimeter. That's pretty small. It's about as big as my phone. That's a pretty small volume element. Well, even for coarse grain rocks, that's probably got about 1,000 grains in it and a hell of a bunch of pores. And if you average the properties in this element and that element and that element, you're going to find that for a lot of sedimentary rocks, this is a reasonably good assumption. Surely at low seismic frequencies, what are the wavelengths of the seismic? At 100 hertz and 10,000 feet per second, what's the wavelength of the seismic wave? 100 hertz is a period of 10 milliseconds. 10,000 feet per second is 10 feet per millisecond. So 10 times 10 is 100 foot wavelength. So I could volume average over a 10 foot by 10 foot block if I want, and so long as this 10-foot looks like that 10-foot block, looks like that 10-foot block. I'm still okay. All right, and that isn't strictly true. For, well, you look at logs and you know that rock character varies, but it doesn't vary a heck of a lot. It's a reasonably good assumption. It's got to be a closed system. Closed system means no mass transfer is allowed across the boundary of a volume element. So when we squeeze that rock, we're not allowing mass to come in or go out. We're not squishing fluid out and bringing it back in as the wave passes. Continuous fluid phase with a single pore fluid pressure. That's very important. Very important, and we'll talk about this a little later and bring it back up. But basically what this means is I have one pore system that's continuous so that I can define a pore fluid pressure everywhere in the rock. A single pore fluid pressure. Speak up. The shear modulus, as I put it in the equations before, is assumed to be independent of the pore fluid. Jim Berryman has since shown that this is really an assumption. It was an obvious assumption that Gossman made. Since fluids can't support shear waves, how could they add to the shear modulus of the matrix?
Is the assumption of a closed system, is that consistent with it being porous? Because I mean, there has to be, the water has to move around within.
Yeah, good question. And the answer is, you'll see experiment. So let's wait for that question. It's a matter of time constants. And in which the body forces only, and not surface forces, are considered. Okay, that's important. I'm not considering surface tension here. We're only looking at body forces on the rock. If you then do the static analysis, you'll come up with those equations I gave you in the last slide. Okay, we're going to go in and after lunch and talk about some details of Gossman and what it means and how to understand it. But what's important here in this part of the development is Gossman's equations do apply to porous and permeable reservoir rocks. They are derived in a low frequency limit and they are appropriate to describe response of exploration seismic. They predict that VP depends on the elastic properties of the solid components, and those are the pore fluids and the matrix of the rock structure. And this is consistent with the experimental evidence we have just seen. Why? I didn't say anything about, well, we got the architecture in there already, porosity explicitly. We have the fluid and solid elastic property dependence in there explicitly. We don't have stress in there explicitly. Where does the stress come from? The stress enters in the matrix elastic constants. And in fact, Gossman's next paper in 1951, what he did was say, look, I'm going to consider a simple system where I'm going to put a bunch of elastic spheres together in close packing. Okay, I'll make a row of spheres, and then I'll put in depressions, more spheres of the same size, all of the same material. And I'm going to consider the deformation of that body as I load it with a stress. How much does it change? And of course, he used Hertz theory for the contacts of the spheres. And what happens is that the spring constant, the K, the modulus, increases as the 1/3 power of the, the spring constant K has a 1/3 power, I think that's right, of the differential stress. Differential stress is what is important. And so he found that there was a stress dependence, and that stress dependence for that particular geometry, that particular architecture, was something like what you saw on that slide. It's like a power law, so it would increase most for the lowest differential stresses in the linear scale of pressure. So it is consistent. This formulation is quite consistent with the experimental evidence, which in fact came a little later in the case of porous. It's a good place to stop. I think that's it. Well, not quite. Oh, this is important. Let me see what else there is here.
We have
Okay.
lunch is at 12:32.
Okay, good. So I've got time to talk about these. There's just 3 more, and I want to talk about we used to have this in the next lecture, and we moved it up here. I'm sorry, I should have indicated. The fluid substitution logic we're going to pursue next is, I've got two equations. I'm going to go back to those equations. Two equations and two unknowns. So let's talk about these a little bit. If I know all these things on the right-hand side, I could predict what the velocities are, right? That's pretty easy. We just got done saying there's a table for these grain properties. And you're going to see later today that it's possible also to estimate the fluid properties. A little more complicated, but possible. We'll go through some of that. So consider the rho sub f and the k sub f as known for all the fluids of interest in petroleum or hydrocarbon exploration. We're going to estimate porosity somehow. We're going to have to do that. We don't know what it is a priori, but if we have logs, that's what that bottom, remember that thing down there about properties from the logs? That's where we're going to get the porosities from, systematic variation of porosities with things we can predict from the surface. So maybe we can estimate the porosities. It's important what we're going to need. What can we not get out of a table? These guys. Anybody want to tell me what the matrix modulus is of a particular structure of a porous rock? I mean, Gossman's wrote a whole paper just considering one that isn't anything like any rock you've ever seen, not even a Nulitic limestone. Okay. It's not something you can get from first principles for complicated geometries. So you're going to have to use some kind of empirical relations, and a lot of people have tried to do that. It's not easy to do, but it can be done. But in general, that's not the way we try to play this game. Instead, let's imagine that we know these two velocities when we have some particular fluid in the rock, a fluid, the properties of which we know. Like rock, I got log measurements. Where I got the porosities from, well, I'm also going to have transit time measurements, that's velocities, right? And imagine for the moment that I have shear velocities too, which you can get, not so easy, but you can do. It's not as common. Well, then I could solve these two equations now. If I know the porosity, I can look up all these other things. I know these, so I can solve these guys for sigma sub m and k sub m. What do we know about sigma sub m and k sub m? They are properties of the evacuated matrix. The evacuated matrix doesn't change. Its properties don't change. The architecture doesn't change. When I pull one fluid out and put another fluid in, so long as I'm not putting in an acid or something, dissolving rock. Okay. So if I take the water out, the brine out, and I stick hydrocarbons in, I get to use these values I now have determined for that rock. And now I know everything on the right side. So I can compute new velocities of the rock for that second fluid, for that hydrocarbon fluid. And the prescription of how we do that is what we're going to talk about this afternoon first.
Oh, you want to use the arrows too if you want to go.
Get there. Get there slowly, sure. Well, that's great if I have a shear velocity. Now we're going to do, how do I solve one equation of two unknowns? I don't have shear velocity most of the time. I only got one equation. I got the velocity, the p wave velocity from the logs at a porosity. Well, what do you do when you got two unknowns and one equation? What do? You can do two things. You can punt, or you can do a variational calculation, which is typical of what people do. Say, well, let's see how the solution varies if I tie one of these babies down and just assume different values for it, and see how much it affects things. How sensitive is the answer to each of those variables? So what we're going to do is do that. And now I'm going to go back. I figured this baby out. And now I'm going to say something about why we chose to write this equation in terms of K and Poisson's ratio. Because Poisson's ratio is limited between 0 and 0.5, so it's relatively easy to span the whole space of possible variation. Most of the other elastic constants, you have to go from 0 to infinity. Okay? So that's a convenient way to do this. And don't ever let me catch any of you people saying that nature isn't kind to us. Because nature is kind to us. It turns out that for sandstones and for many other sedimentary rocks, for some kind of sandstones, for most of the ones of interest to you, high porosity sandstone, the answers are not very sensitive to what the shear velocity, what Poisson's ratio is, sigma sub n is. That's very important. That is in the range where sigma sub m's turn out to be. We know something about the sigma sub m's from laboratory measurements on rocks, where we can propagate both P and S waves. And now we get the ratio of the two velocities, and that's directly related to Poisson's ratio. So we know from measuring these in dry rocks, or from backing them out of these two equations for wet rocks, which is what we really do, something about the values for sandstone for this constant. And so therefore, what we want to guess. But if you guess wrong, so long as you're not too far away from this values I'll give you don't make a big mistake in the difference in velocity you will get by following this substitution procedure I just told you. That is, this one. Assume a value for sigma sub n, use it, solve the equation for beta. Beta is going to vary between 0 and 1. It's dimensionless, right? It's just a scaled bulk modulus of the matrix. Use this value of beta and the assumed value of sigma sub m to solve for VP with the new fluid, and you only get small errors in the, I'll say in the VP, but certainly in the VP, but not even big errors in the difference of VP. Reasonable values for sigma sub m. This is something you want to remember. For porous sandstones, 0.15 to 0.2. For limestones, it almost doesn't make much difference what porosity you have. 0.3 is a good number.
Just on limestones, that's oolitic limestones, that's, you know...
Diagenetically altered, making it 0.27 to 0.3. That's what it is. Dolomite's a little lower, if I remember. Dolomite's like 0.2725. But not sensitive to porosity. Okay. So I said, how do rock velocities depend on the properties of the constituents? And in particular, how do they depend on the pore fluid properties? And now I've just told you that's what we're going to talk about this afternoon. And I'm going to show you some results of using Gaussian equations and going through those fluid substitution calculations and why you get those results. We'll talk about those equations in some detail and then look at some experimental evidence for whether they match experimental data.
Yeah, one thing just sort of to accentuate again some of what Dave was just talking about in terms of nature being kind to you, that, you know, and the way to think about it is there's very little,
You can't record
That there's very little sensitivity to what sigma sub n is. It's all with respect to beta, okay? And you'll hear us talk about beta, beta, beta as we go on. That's the thing that really determines the particular rigidity of the rock and the amount of the Gaussian substitution. And so that's, ends up being, what, again, we're going to focus on, going forward. And again, that's the reason why we, wrote it in that way. And another side benefit of this is that you do have to be careful with respect to VP-VS pairs, that for some reason if you have an unreliable or a shear log that's off, that if you look, that it can actually get or imply values of sigma sub m which are fairly unreasonable, okay? So that it turns out, again, here that because of nature being favorable to you, when it comes to Gossman substitution, that you, in certain cases, are better off using the sigma sub m rather than just, you know, and putting that fixed value, rather than using the value coming from the shear log.
We'll talk about that a little more later and why that is, why that can occur.
But anyways, again, yeah, that's, and we'll be coming back again to this equation and its different, you know, sensitivities, you know, sort of later on this afternoon.
First thing after lunch.
Yeah. Did you want to go through some of those Angola things, or just go ahead?
No,
and break
I
them
don't.
down?
I want to talk about the equations first, then they'll be more understandable. That's why I want to push
Okay.
that.
And so we'll go ahead and, I think they probably have lunch just about set up by now. And,
It's a good bathroom break.
yeah, and then, do you want to go and then start after lunch?
Right.
Probably what, 1 o'clock? or-
Well, I would certainly not, yeah, 1 o'clock's fine.
That's about 40 minutes?
Oh, it's fine.
Okay.
Between the grain bulk modules on the matrix and the matrix bulk modules. I understand matrix bulk modules also.
Grain bulk modulus.
Repeat the question.
Yeah, I'm sorry for the recording. Ian asked the question, what's the difference between the grain bulk modulus and the matrix bulk modulus? And he said he understands the matrix bulk modulus, which is the modulus of the evacuated rock. If I put an envelope around it, and I had a perfectly rigid envelope, and I squeezed that evacuated rock, and I looked at its volume change in response to a certain applied stress, hydrostatic stress, that would give me K sub n. The grain modulus is take the mineral of which that matrix is composed and tell me what that solid mineral's modulus is. Okay? That's K sub G. Some people use K sub S, but then that gets confused with adiabatic moduli, which subscript is S, etc. So each guy that has written uses their own choice of terminology.
Let me just go and ask another,
Beta is big. Mike was talking about it. My catchphrase for that, your slogan, you know, you like your campaign slogans, we got an election coming up. Everybody's got to have a slogan. Beta is big, remember that?
this is sort of, I mean, I'll ask a particular sort of question sort of based off of, there's a competition in the US for children called Odyssey of the Mind. And every year, one thing they always try to do is build a very, you know, efficient balsa wood structure. Okay? And if we went in, okay, and that what we're looking at, and that the modulus that we're talking about of the grain here would be the modulus of sort of pure balsa wood, okay? And let's say we had two teams, right? And one, you know, went and built a particular, the size of the structures were the same, but we had one which built a really good structure and could hold a lot of weight, and another one which didn't do a very good job and couldn't hold very much weight, okay? Which one ends up having the higher beta in this case? Is it the one that's well constructed or the one that's poorly constructed? The well-constructed
The
one.
stiffer one.
It's stiffer, it's closer to having a pure block of balsa wood, okay? Comparing a pure block of balsa wood to the particular structure that they end up having. So more efficient structures have higher beta, okay?
Anybody else? Yeah, John.
The isotropic porous material, this beta, given it's the matrix to the grain thing, in some sense it measures how, it's a measure of how much of the space is taken up by pores. It should depend directly on porosity.
It does. It depends on porosity,
Yeah.
but indirectly, not directly. There's no easy way to formulate for any kind of structure, for any and all types of structures, how that dependence goes. You can do it empirically. but
Even though it's isotropic.
even though
Because
it's
if it wasn't isotropic, you might have cylinders, you might have...
It's macroscopically isotropic, yeah.
Well, it depends on, yeah, the details of the structure. We just, as I was talking about, is it a well-constructed, poorly constructed? One thing that does vary fairly highly is whether or not the balls are all, if you have a particular assemblage of balls, right? Or are those balls all the same size or not? If you can have a structure with the same porosity, but if you use a lot of different ball sizes, you find out it's a less efficient structure than if you end up using all the same size. You find it's a more efficient structure, for instance. So there's an overprint of architecture. You know, there are two, on the architect, there are two types of architecture. One is, you know, sort of root porosity. The other is kind of the style of the assemblage, or something like sorting. So the two actually go together. The primary determination is porosity, but things about fabric or efficiency of the structure or sorting end up having the next order effect that comes in, which isn't non-trivial in certain cases.
Thanks for that.
I said I'll use a little more time here, need a little more time. I sort of said in passing, beta is going to go between 0 and 1. It's a scaled matrix modulus, scaled to the grain modulus, of which the structure is composed. So just a simple thing to think about. If I have no porosity, as John is thinking, what's the matrix modulus?
That's the grain modulus.
If porosity is 0, I put the cellophane around the solid and I squeeze it and it's a solid. So K sub M equals K sub G, and K sub M over K sub G is 1. And if I have 0 porosity, well, then I don't have any structure, so I don't have any matrix modulus either. But I don't have to have 0 porosity to get to 0 matrix modulus. If I have, Mike's thinking of, I heard you think, and I did earlier, about an assembly of balls when I was talking, Gossman and his post-impact spheres or whatever. If you have a suspension of balls, and they aren't even touching each other, you don't have a rigid structure. 0 matrix modulus. K sub M is 0. Therefore, K sub M over K sub G beta is 0. Beta can't be less than 0, because then you would have, when you squeezed on something, you would have to get bigger. Since K sub G is always positive, right? So it's possible.
Yeah, nonlinear fluid.
What's that?
Could you have a nonlinear fluid when you squeeze the feed?
Yeah, this is far out thinking, but the answer is no. And the answer is you might conceive of a material in which somehow K sub M would get bigger than K sub G. I think it's very hard to conceive of such a thing. I haven't come across such a case, but of course I haven't taxed my imagination worrying about it, because as you will see, betas close to 1 are very interesting for us in hydrocarbon.
Yeah, well, they end up being more important, obviously in the hard rocks, because the sort of definition of a hard rock is beta close to 1. Okay. Yeah, one thing too is that in one particular empirical fit that people like to use is to go and say that you end up having just a difference between some sort of porosity at which things become sort of disconnected. I mean, if you throw a bunch of balls together, sort of what's the porosity at which you sort of get? If you have a porosity greater than that, they are disconnected. And you sort of use this to the K with an A out in front.
Yeah, that's mine.
Yeah, and I mean that's it's a fairly common empirical fit that people use. And they, by the way, that you'll go into the Stanford school they build up a whole industry around this, because they call this a critical concentration, because those of you familiar with critical theory, it's the form of Lincoln's bank.
But they have no exponent. Their exponent is 1.
But then, but this is normal critical exponent.
Right.
So.
What's the typical value of beta, say, for a sandstone reservoir rock?
Well, we'll talk about that. Right after lunch, you will see. We'll see some typical values. Okay? And different rocks obviously have quite different values. You saw that slide that I showed twice in the factors that affect rock velocities, the sandstones. at zero stress, different porosities, and you saw that the velocities varied for the dry rock even. Now I'd have to look, but for the water saturated rock, I remember something like 8 to 18,000 feet per second or something like that. Well, suffice it to say that the propagation speed for compressional waves and isotropically averaged quartz crystals with no porosity is just under 20,000 feet per second. So if you've got 18,000 feet per second velocity in a low porosity rock, which we had over here on the left-hand side of that slide, you've got something with a beta that's pretty close to 1 after. But betas can get very small.
I thought how you could measure a beta greater than 1, if you got the assumption, if you got, like the mineral was not isotropic, but you assumed it was isotropic,
Yeah,
and then
oh yeah,
you get
those
it
kinds of
with-
things, where you violate your assumptions,
Yeah.
or that game's over. But that's not a funny thing. That's really not a funny thing. We make assumptions all the time that aren't true. Okay, and I said we proceed from the simple and more complex. That's the right kind of thinking. You should be thinking about under what circumstances would I make mistakes? And that's a very typical kind of mistake you could make. There's feldspar grains in the rock, and I'm using silicon dioxide as if the sandstone was all silicon dioxide. What should I do if I've got 20% of the grains are in fact feldspar or certain kind of feldspar or whatever? Look at your table. That's what to do. And then we'll talk about that. Okay, I won't talk that. Mike, where's the food? I want to talk about this equation. We now know we can solve this guy, since we know that we won't make a big mistake and we make reasonable estimates for the surface amount. I want to think about what happens in this food substitution process we just finished talking about before lunch. And so there's two factors in this upper equation. So let's start, we'll talk about this one too. Let's talk about this one first, it's easier. Forget all this. E squared equals mu sub m over rho. That's pretty simple. What's going to happen when I put a more dense fluid in, less dense fluid in for a more dense fluid? So brine is a dense and incompressible fluid. Water, that's pretty stiff. Got a pretty high K for a liquid. But gas or oil is lower density. And also, they're commonly, the density and the bulk moduli are related fluids. The higher the density, the stiffer the spring. Okay, the volume of the spring, so the higher the bulk modulus. So the gas or oil will be less dense and also lower K than brine. That's what we're going to do. Substitute in a hydrocarbon, which is more compressible, for lighter and more compressible for brine. Let's think about what happens to this equation. Mu sub m doesn't change. It's a property of the matrix. Doesn't have anything to do with fluid. So the only fluid dependence comes here. Well, let's look at that one. That's rho g times 1 minus 5 plus rho f times 5. The change is going to be all in here. Right? Well, let's look at the size of these terms. Porosity, you know, at the sea bottom, porosity is like 40% or something. When you first drop the stuff out, in the first few feet, it gets down to very a reasonable porosity. So think of porosities in the 30 to 40% range here. Those are the softest sediments you're going to find. Even for that soft a sediment, this thing is 0.6 to 0.7, right? Times 2.65 for quartz. Well, let's make it 2/3 here and 1/3 there. It's easier. 2.65 times 2/3 is 5.3 over 3. What is that? Roughly 1.8, right? 5.4 over 3 would be 1.8. So 1.8 grams per cubic centimeter from this term, which doesn't change. And over here, when I have the brine in there, I've got 1 times 1/3, so that's 0.33. So that's about a sixth of what this is. And when I put gas or oil in here, I'm still gonna have a little left. This term's still gonna be finite. It may not be big, but it's gonna be finite. So I'm not gonna change the density very much. And the velocity depends on the square root of the inverse of the density. So, gee, I'm only gonna change the density by about 10%, maximum. And I take the square root of that, it's only gonna be 5%. Right? So 5% isn't very much. And which way is it gonna go? The density's gonna go down when I put the gas in, or the oil in for the water. So it's in the denominator, so the shear velocity is gonna go up. Right? So when I substitute hydrocarbon for brine and porous rock, I expect the shear velocity to go up, if Gossman's right, and not very much. Okay, let's go to this equation. I have a similar term. I have this density in the denominator and something that doesn't depend on the fluids in the numerator, so we already know what that factor does. It's going to want to make the P velocity go up, but it has the same limitation. It can't go up very far because of the ratios of these two terms. Okay? So let's look at what's inside. What do we got here? This thing only depends on the matrix. Doesn't have any fluid dependence. This thing doesn't depend on the fluid. Doesn't depend on the fluid. This whole first term, whatever it is, doesn't change when I do the fluid substitution. What does change? Well, not this. The denominator changes, doesn't change here. It changes right there. Porosity doesn't change. That's where it changes. Let's see. I put in the hydrocarbon, that's got a lower K than the brine. Lower K means this term's going to get bigger, this factor. That means the denominator's going to get bigger. That means this term's going to get smaller. This term's going to stay the same, so the thing in the bracket's going to want to get smaller. So what have I got? I got VP over here. This term wants to make it go up when I put the hydrocarbon in. This factor over here wants to make it go down, so they're competing. So which one is going to dominate? When is one going to dominate the other? Well, the first thing is, this one, I'm never going to get much out of it. It's going to want to go up, but it can't go up very far. So let's think about this beta for a little bit. Beta can go between 0 and 1. Okay? And suppose, like we said, you had no porosity at all, then case of M is case of G and beta is 1. So let's think about low porosity rocks where beta is close to 1. What happens? This term is big because beta is close to 1, but this term is very, very small because beta is close to 1 and the numerator is very close to 0. So no matter what I do to this, I can make beta, if beta is close enough to 1, it's going to be small compared to this term. And this thing is going to dominate if I get it small enough, get it close enough to 1. Let's go to the other extreme. Let's think about the other end. Beta close to 0, what happens? And this guy gets little, and this guy gets big. Then this thing can dominate. And look at what happens. This thing, Kg is always bigger than Kf, lots bigger. Remember I said 55,000 psi to squeeze that 1% for silicon dioxide, but only 4,000 psi for water? So this is a big number, 15, 16, something like that. This number is 0.3 or 0.4 for a low beta rock. So that's 4, and this thing is 5. So I got a pretty good size term there. This thing can change enormously because this could go to close to 0. If I put in gas, a low pressure gas, it can change a great deal. From 15, if you go to 30 or 40, I can change it to make it a 10, or change it by a factor of 2, then I have practically nothing over here. So this whole brackets, when beta is very small, will dominate this term, which can't change by more than 10% or something like that. So now, having said all that, let's just do the calculation. Let's do the calculation and look at what some things look like. We don't have too many of these to do, so there we go. I'm going to show you a series of plots which are the result of a typical plastic case, and I did it for reasonable true reservoir. Now, I haven't talked about certain things that go into this calculation, but I will within the hour. So don't worry about this up here, but it is for a reservoir with water saturation of 0.2, and I haven't talked about how to do that. That's not how to do it. It's quite transparent. We're going to plot everything against the brine saturated velocity and the parameter we're interested in over here, which is beta in this case. Right? Now, why did I do that? Before I do that, I'm going to use this trick that Mike told me I can do. And the reason I did it is because what do we need to solve this equation? We need VP now and porosity. We need a pair, VP and porosity, in order to solve for beta with a known value of sigma sub m and all these other constants of the fluids and the solids. And then we've got the beta. Then we stick in the new K sub F, rho sub F, the new fluid, hydrocarbon, and we calculate using that beta what VP is. So we got a new VP, a change in VP. Right? So everything is going to be in terms of VP and porosity pairs. And I could have done that as a contour plot. You geologists all know like contour plots. I could have done that in a contour plot. It's a two-dimensional space. I could have put porosity here and velocity, brine saturated velocity here, and drawn contours of what beta looks like. I didn't do it that way. Sorry, I did it this way. Velocity, beta over there, and different curves for different porosities. So here's porosity 0.1, porosity 0.2, porosity 0.3, porosity 0.4, and above this, you really can't get. What's that say? In other words, somewhere up here, you have a suspension. You don't have, you go to 0. You might get a solution, but you wouldn't get, it wouldn't be meaningful. So this is, in essence, non-physical region. No rock exists that's made out of silicon that has a velocity of 8,000 feet per second and a beta of K of 0.6. Not made out of silicon dioxide. Now we're going to superimpose on that a trend from the deep water Angola. We know what VP and phi are as a function of depth from log velocities at Angola, which have been collected from more than one well. They're systematic. And I didn't label the depth over here, but it's not too hard to figure it out, is it? This is the deeper, and this is the shallower end. And it crosses, and how do I know that? Because it crosses the porosities, and as I get deeper, I go to lower porosity. Down here at 10,000 feet below the mud line, I'm down, about 13% porosity or something. At 8,000 feet, it's pretty close to 20% porosity. And over here, I'm very shallow. I can't remember whether it's 2,000 feet, I think, below the mud line. And you're almost at 40%, above prism, that's for sure. Okay, so what's the beta? Now, you wanted to know beta values, typical beta values. Here's some typical beta values for a real rock. What's the beta value? Shallow. 0.02, something like that, right? What's the beta value at 8,000 feet where you have still a 20%, 18% porosity rock or something? 0.22, something like that, 2.3, something like that. Okay, that's this particular trend. You could find a trend for a different basin and a different reservoir rock, and it will superimpose on these curves in a different way. But those are some typical betas for a recent or deep water sedimentary basin, sandstones. Let's look at another one, another property. Since I'm solving Gossman, hey, I could look at the gas saturated VP for my 20% water saturation rock against the brine saturated VP. And this dash curve is, if they were equal, that's what it would be. And what happens? Well, when I have these low betas down here with the low velocities, low VP, brine saturated, when I have those, I get a big difference, right? Here's the brine saturated velocities, 8,000, and down here I'm at 6,000. I got a 2,000 foot per second difference. When I get up here, I cross zero for certain of these rocks. That means that K sub G over rho term is dominating when I get up here. Okay. No such rocks really exist, though, I can tell you that. I'm not saying you will get that effect. This is what deep water Angola rocks look like. Okay. Big effect, shallow. The deeper I go, the lesser effect. Here we are at, whatever that is. This one's 0.1, 0.2, so it's this. Something's wrong, and one of these two curves I plotted is wrong because this has to have the same porosity at the end point, right? So when I plotted this overlay, the last one, we were on this side of this curve, now we're on this side of that curve at 10,000 feet, so I made a mistake somewhere. So maybe I can fix that. Anyhow, you get the picture of how things look. This is a much smaller difference at this lower porosity, higher beta down here at 10,000 feet than at 2,000 feet. Very low beta. Okay, what else can we calculate? We can calculate the interface reflectivity. We started with the brine saturated velocity, and now remember our picture, reservoir, brine saturated down dip, up on top we have gas saturated, and I said, hey, it's that interface in the reservoir rock, that fluid interface in the reservoir rock that tells us whether we're going to have a big effect or not. So let's calculate the reflection coefficient at that fluid interface. We know the initial brine saturated velocity, and we just calculated the gas saturated velocity, and we got the densities too. And we know the porosity, so we can calculate the densities. So we can calculate the reflection coefficient at the fluid interface. And this is it. And again, these are our different porosity curves. And this one, there's Angola. Deep water Angola. Now, which way does this go? Low velocity, low VP is low beta. That's this end. This is 2,000 feet depth. This is for 10,000 feet depth over here. Now it's at whatever that is, 0.2, right on 0.2. So I'm fairly close with those curves. The first two, I need to jiggle one or the other. And this is just an artifact of, this is just, the fact that this is closer here than either here or here is just because I get them every 2,000 feet. That's really a smooth curve. You should worry about that. So what does that tell you? It tells you shallow, I have a huge change in the reflection coefficient. Huge reflection coefficient, 0.4 for crying out loud over here at 3,000 or 4,000 feet. 0.2, that's monstrous. That's a big reflection coefficient. Typical reflection coefficients, if you looked at shales and sands and lots of reservoirs at common depth, they're like anywhere from 5%, 0.05 to 0.1, somewhere in that range. That's not uncommon for long lessons in soft rock basins.
So what that means is you lose a lot of energy from your finger.
Here, you would, but not as much as you might think. This is an amplitude reflection coefficient. And the energy goes as the amplitude squared. So, when you're up here, yeah, you lost a lot. But even at 0.2 or 0.3, not so much. They lost 10% or 5% of the energy. Otherwise, you would never get reflections that from deeper horizons. Okay, so when are we gonna have, we started saying, when is this stuff all gonna count? When can we take the shortcut and be thinking DHI tells us things that we, about the answers all three of the classical exploration questions? Well, we gotta have some other clues, but we got some pretty good idea here. Okay, so I'm gonna start that business over. I got both velocities, the gas saturated and the brine saturated velocity, so I can calculate the transit time difference per two-way transit time difference now for my seismic per foot for the gas saturated rock less the travel time through the brine saturated rock. And that's what we're doing over here. Two-way travel time change in microseconds per foot. And here's our curves that are calculated from the Gaussian equation. Two-way. Tyler says what? Oh, well, that's a mistake. Thank you, Mark. It's two-way. And so, and this is the answer. And down here, you notice that this one now we have 0 on here. It's a scarcity product. So, what do we see? Well, we see what we knew we were going to see. We see that when there's that big change in velocity and the wave speeds are very low, well, then we're going to get a big effect in transit time. And what is this? What is this? 600 microseconds per foot. What the heck does that mean? 0.6 milliseconds per foot, two-way. Got a 100-foot thick reservoir? That's 60 milliseconds. That's easy to measure. That's an easy sag to measure. What's this over here? I'm down at 8,000 feet. I now have, well, a little over 100. So 120 microseconds per foot. A 100-foot thick reservoir, 12 milliseconds. Barely detectable in most seismic data. You might be able to detect it, wouldn't be easy. Okay? So keep that in mind. When you have very soft rocks, very low beta rocks, a consequence of the hypothesis that you have a possible hydrocarbon reservoir, there are a lot of possible consequences. You ought to check for all of them. One of the possible consequences is you will have a sag on the reflectors beneath the hypothesized reservoir compared with the conformable horizons above the reservoir, shallow. So if you do isochrones, you say, wait a minute, I'm seeing a bump. Okay. So here's my shortcut. Quantitative seismic amplitude interpretation provides answers to all three questions in certain restricted cases. Exclamation point. Correct the slide, make a note of that, please, Mr. Gill. I gotta correct that slide, Mark. Thank you. What are the conditions when you're likely to be able to make this shortcut? I hope now you got a pretty good idea. If you believe gossip, and we're gonna show some evidence for it next, but if you believe it, what are those conditions under which you might expect to be able to take this shortcut?
Isotropic media.
Yes, but talk to me about beta. Beta is big. Talk to me about beta. What are the conditions?
Low beta.
Low beta. When do you get low beta?
Soft rocks.
High porosity. That's the answer, right? High porosity, soft rocks, right? Soft. We call them soft. Low acoustic impedance, low velocity, low brine saturated velocity. Okay. There it is. Propitious circumstances. Fluid substitution results in significant seismic amplitude anomalies only in relatively soft plastics with substantial porosities. In such settings, and this is very important, seismic amplitudes must not be ignored. If you do your trend curves on your logs and you say, holy moly, I've got 8,000 foot per second rocks down here with 28% porosities. I'm going to do a Gaussian calculation. You come up with, gee, I ought to see 25% reflection coefficients. If I put gas in that material, and normally I'm looking at 8% reflection coefficients between my sands and my shales. I turned in my velocities right from my log. Say, I have soft rocks. I should see big anomalies if there are hydrocarbon accumulations. I'm looking at a lot of seismic data here, perspective area. I don't see any bright spots. First thing goes off in your mind should be, how have they processed this data? That's the first thing you think of. Make sure that the amplitudes have been faithfully preserved in the processing sequence. And if so, and you don't see anything, and you should see something, that's pretty condemning. It means you probably don't have big accumulations at very least. You can't ignore them. In harder rock settings, with lower porosities, higher betas, and still, however, completely acceptable reservoir rocks. You could have an 18, 15% porosity sandstone with nice permeability, could be a beautiful reservoir, and you might not have any significant I won't say any significant. You might have a Gossman reflectivity interface, or reflectivity like 8 or 10%, which is about like what you see on a normal reflector. So you double the amplitude of the reflector. There are a lot of things that'll double the amplitude of the reflector. As you'll see when you start talking about trend curves, you're gonna have different kind of rocks, special kind of tuning. There are a lot of things that can give you smaller amplitude effects. So when you're in that situation, it doesn't mean your prospecting is over, but it means you're not going to be able to take the shortcut very easily. Okay?
Are you going to talk about the false positives?
Oh yeah, we'll talk about it. We'll talk about it. Lots.
But also, that's, I want to sort of highlight that last statement of the day.
This one?
When you sort of say in hard rock settings with lower porosities, you give a bit of a teaser in that when we go into hard rock
yeah.
settings,
Still
when you cannot be able, or it's more difficult to be able to see what the Gossman effect is in terms of hydrocarbons. It turns out, though, that you can tell a lot more. It's sort of why they used to call the group lithology and fluid prediction. You not only are going to be able to predict fluids, but when you go into the lower porosity areas, that you end up finding that the amplitudes end up being much more representative of what the porosities are. And we're going to show you that in terms of the sensitivity.
Yeah, that's a good point, Mike.
Coming up.
Very good point. A very good point. We talked about what affects velocities before. You saw the sandstones and the architecture, and porosity was a big thing. And in many situations, finding the sweet spots in porosity makes all the difference between a good reservoir and a poor reservoir. And let's say at 10%, a place where you have 10% instead of 6% porosity gives you good permeability, you have a reasonable gas. So it's very important. You can still use the amplitude. You simply have to revert back to the classical methodology of logic. And among that methodology of logic is there a reservoir rock? And now you're talking about porosity difference.
And it ends up just informing the reservoir quality. It's actually very common in carbonate reservoirs that you end up looking at the amplitudes as a representative of better reservoir quality.
So you don't lump Cascade, Chinook on that report?
No.
It's not hard rock? Low porosity?
It ends up being that the predominant effect ends up being, it's kind of odd at Cascade and Chinook, the dominant effect ends up being an architectural difference in the sorting, and that the porosity ends up being ends up getting very confused with the differences that come from the sorting, as it turns out. So that's a totally sort of, it's actually kind of bizarre. But it turns out, though, that like the carbonate area that we've gotten interested in, the eastern Gulf of Mexico, the Saque region, that there it ends up being that the amplitudes are a very good indication of porosity and whether or not you're in the fluidic fore reef versus the core of it. So actually there it ends up becoming very important.
I can talk to you offline about cascade and shield, because we've written several papers on that in a lot of physics, and it ends up being interestingly unique.
Okay. So we talked about this before lunch and after lunch as a combination. And Gaussman's equations can only predict the effects of fluid substitution. Well, that's not quite right, but in the most common use, that's what it tells you. This requires knowledge of the properties of solids and pore fluids, as well as of porosity and VP. Boy, this is what you want to remember. We're going to go through the rest of this. We're going to go through this stuff this afternoon. This is what you want to remember. You're going to have to come up with porosity VP pairs. Okay? VS need not be known to calculate the fluid substitution effects on VP to within reasonable accuracy. Gaussman predicts VP will decrease and VS will increase when hydrocarbons replace brine. This is important. VP over VS will decrease when I substitute the hydrocarbons in there. For AVO, that's going to turn out to be an important statement. Large reflectivity changes are possible at fluid interfaces in soft rocks, in low beta rocks, high porosity rocks. Measurable transit time changes will occur in thick hydrocarbon reservoirs when you have this, soft rock.
Most of the time, you use gas as your example.
Yes.
It's easy to visualize, and it's quite different
Yes.
from brine. But
Oilless.
oils.
The answer is, we're going to look at that in a moment, actual properties, but the answer is, I use gas here because it's sort of the extreme case. And so you should think of that as bounding. The answer is, oil, as you know, has densities that are closer to water, typically something like 0.7, 0.8 in that range. And turns out bulk moduli that are like 1 as opposed to 2.5 or 3 for water in some units. So you wind up with significantly less effects in oil, but still the same character of effect. That is, in the most porous rocks, you'll get the biggest effect, and it's not an insignificant effect if the betas are low. It's detectable.
Yeah, well, and also just sort of a simple back envelope to just sort of know what the size of the effects are. Shallow, the gas to brine sort of reflectivity ratios aren't uncommon to be 4 or 5 to 1. Oil 2 to 3 to 1. If you go down deeper, you'll get oil at, let's say, 50% to sort of 2 for 1 brightening, or gas will maybe be a 3 for 1 brightening. It comes about because the gas ends up compressing to be remarkably sort of similar to oil as you get deeper. Once you get up, you take gas and you get up to 10 to 20,000 psi, it starts being a third of a gram per cc, and probably getting close to even 1,000 foot per second, compared to brine, which is 1,500 foot per second.
Okay.
Can I ask a question? You have shown earlier some graph where the velocity is very dependent on the pressure.
Yes.
But this Gauss formula does not explicitly have pressure in there.
Were you not here? We talked about this just before lunch. Okay, I said that, specifically drew attention to it, that there is no pressure directly in the Gaussman equation, but that it is not inconsistent with that result because beta depends upon, or can depend upon, stress. And then I remarked about how Gaussman's next paper, after the paper in which he derived these equations, was to try to calculate from first principles with a packing of spheres, remember, what the beta would be from first principles. So he puts a load on the spheres and calculated beta, and I said the beta he got went like delta P, the differential pressure, to the 1/3, if I remember correctly, power. So he calculated with Hertz contact theory that an assemblage of uniform size and composition balls would give you an effect that depended on differential pressure, not just on confining pressure, and that would increase roughly like what we see over here, what we saw in the empirical data. So the pressure dependence is in the matrix modulus.
Just remember, it can change dramatically, going from surface conditions to 4,000 or 5,000 PSI, which is maybe a couple kilometers deep, a kilometer or two deep. That you remember that these betas go from 0.2 to 2, I mean from 0.02 to 2, so they'll change by a factor of 10, and that directly goes over into velocity.
Okay, I'm gonna say one other thing. This may confuse you a little bit. This is pretty good. This kind of thing can be used at relatively high differential pressures. And it fits the empirical data very well at high differential pressures. Where, you remember how that curve flattens over? The curve of velocity versus pressure, confining pressure or differential pressure. You know, we could tabulate it that way. That curve rolls over so that at higher pressures, the velocity change for 1,000 psi change in pressure isn't as great as at lower differential pressures. Well, this thing doesn't take account of pressure explicitly. It would have to take account of it only insofar as how porosity was related to differential stress. But at high differential stresses, where that curve is fairly flat, the stress dependence is not so important, and this works very well. This kind of thing works very well. Okay, we'll talk about